So my name is Romain Viala. I'm working at the ITEMM, which is Institut Technologique Européen des Métiers de la Musique. It's an institute where guitar makers, wind instrument makers, brass instrument makers, we teach instrument making for different kind of instruments. No quartet instruments. There is also some parts for the sound and also for the pianos. So it's an institute where it's mostly dedicated to teaching, but also there is a small cell with two researchers, where we perform a bit of research and a lot of transfer. So our work is to transfer what is currently seen and what are the main outputs of the academic research, and we transfer it to instrument makers. So during this talk, I will I will present some activities about virtual prototyping, but also I will sometimes sketch to show, for example, a 3D scanner that we use that is affordable, different methods that are really pragmatic and can be used in workshops. So, beginning of my talk. So I will mostly deal with virtual prototyping and about the dynamics. I do not deal a lot with acoustics, which means the propagation of the sound in the air, mostly the propagation of the sound inside an instrument, the vibrations, and also the virtual prototyping, which is a method to numerically draw an instrument, and then to evaluate what we can do with this model and what this model predicts. The global topic is towards the model-based decision support tools for string instrument making. This was also the subject of my PhD. And now so I will present you a lot of work I made during my PhD, and switching to what we are currently doing at the ITEMM, like, for example, new tools for bow makers or etc. So at the ITEMM, we are considering two kinds of instrument makers. There is the unique instruments made by craftsmen with empirical methods, and also identical instruments made by manufacturers with automatic methods. And we are constantly switching between each point of view. And our problematics for which every instrument maker, if it's a company or a craftsman, undergoes is that the wood, most instruments are made of wood with evolutive and variable properties. And there is also a shortage on several species, tropical and temperate species, and also a cost. So it's not possible to test every samples, etc. And also there is a competitive environment and cheap instruments and more on high grade and low grade instruments. So it's a changing, for example, for piano, for guitars, there's a lot of change due to the different rules and about the wood and different kind of competitive environment. So when we are studying a musical instrument, we have the choice between different approaches. The usual approaches that have been used for decades are the experimental studies on real instruments. That's why, for example, you have seen some tests performed. You measure the current behavior of a musical instrument. You can measure many things. You can measure the sound. You can measure the vibration. You can measure the deflection when you apply, for example, a mass. There is a lot of ways to measure something on an instrument. There is also another method, which is the analytical studies with simplified behaviors, for example, with equations, with different models that are simplified. You can observe some real features of an instrument. And also, this has led to what is generally called, for example, plate tuning, that's an example of application, and experience-based construction protocols. So the idea is to monitor between different steps the properties, like you have seen the frequency of the free plates, and to monitor it up to go to the sound. So this method, experimental method, they are effective, but they are very costly because you have to make the instrument to go to a further step. And it's sometimes very difficult to relate to actual design, which means that when you have the sound of an instrument or the last feature of an instrument, the perception, the sound, it's very hard to relate it to a step that you have done 15 steps ago, because between these the first steps you have made measurements and the last one, there have been a lot of changes, a lot of uncertainties, a lot of variability that has come.
Okay.
This is, well, your usual approaches. The physics-based modeling approach use finite element models, a finite element or other models. It's physical models. It's models that deal with the actual geometry of the instrument that is drawn with a software, computer-aided design software. And in this software, we put some physics, and though we can have some simulations. I will show you just after. So it's very detailed, can be very detailed models, and it can be able to perform, for example, parameter studies like sensitivity analysis, which means what is, if I consider the eigenfrequencies, the resonance frequencies of a violin, like the B1 plus, B1 minus, what is the most important parameter, geometrical or material parameter on this feature? And with this model, you can evaluate this, and we also can evaluate the impact of uncertainties, because there is a lot of uncertainties when we are dealing with wood, and also different making tolerances, etc. So it allows to compute response field, responses, and also, for example, the stress state. When you pull the string on an instrument, what happens in terms of stress in the instrument? So the numerical prototyping leads also to the optimization, and you can, before making a real instrument, you can try new concepts, like you want to change a given F-hole shapes, etc. You can evaluate what would be the impact of this modification on the feature, for example, on the dynamics. But numerical prototyping requires high fidelity models. So there is limits, because the usual experimental and the experimental methods, when you are, for example, cutting F-holes in an instrument and you measure, you cannot put again the wood that you have cut the F-holes in a different shape, and then measure again. It's not possible. So with the model, it's possible, because you can change one thing at a time, and you can go back to a previous step with the model. And also, another limit of usual prototyping is that raw materials and construction time are very costly. And sometimes with, for example, old instruments, you cannot do whatever you want, like, for example, taking a sample of wood to evaluate its mechanical properties, etc. So the virtual prototyping, we will try to understand complex interaction phenomena and the influence of instrument design on dynamic outputs. And this is a way to explore replacement solutions for unavailable traditional wood. This can provide dynamic models for sound synthesis, for example, and decision support for the conservation and repair of musical instruments. So on the right, you can see, for example, a drawing of, there is the drawing of the violin, and also different kind of thing that we can model, like, for example, the resonance shapes, so the eigenmode shapes of the violin. So I will discuss about the different parts, like perform analysis, rank influential parameters, and take into account uncertainties. So what kind of analysis we can make with a model? You have input. You have input, you have a model, and you have output. Your inputs can be the forces, for example, the motion of the string that is applied on the instrument, the relative humidity in the room, or the temperature. Then you have the model. The model here is a drawing with a geometry, material parameter, press stresses, states, a lot of different parameters. And then you have the output. So you evaluate the vibration. You can evaluate the bridge admittances, I've discussed a lot of the admittances yesterday. Or even the sound. So this is a direct analysis. You see, it goes from the left to the right. But also we can use it for the optimization. You have different vibration or admittances or a sound that you want, and you can optimize it to try to, what would be the modification on the model that will lead to what you want at the end. There is also the model calibration. You got a model, but the model is not very good. It's quite, there is a leap between the model and the reality. So you can calibrate the model so it can be a bit better. And also there is another way, is the input identification from the right to the left. And you got, for example, the vibration, the sound of an instrument, and you try to go back by reversing time to what was the force applied on the instrument. So just an example, which is a joke, but you can, with the sound of a model, you can evaluate the relative humidity in the room when an instrument has been played. Okay, it's not possible because it would be the most costly hygrometer and the less precise hygrometer that would exist. It's because between your inputs and between what you hear, there is a model, and a model is false, but it can be useful. But it's very hard to have a good way between what is in what you put in a model and what you have outside. So there is a lot of uncertainties, and we are dealing mostly with uncertainties, and that's what I will be talking about. So the source of uncertainties in the reality, when you have a measurement, when you consider a measurement, you can, for example, measure a frequency on a plate, for example. But the frequency on this plate will depend on many parameters, like, for example, the relative humidity changes, the temperature, when it's an instrument that is played, a musician, because the musician can play different way. The making tolerances. So for example, if you are working with like a tenth of a millimeter precision, a tenth of a millimeter can be very important in terms of eigenfrequencies of the plate. So, and also the wood is very variable. I will talk about the wood a bit later. The wood is very variable. It can have changes in density, stiffness, and damping. So there is a lot of variability on uncertainties. That's why it's very hard in reality to make a link between a feature that you observe and what you have put inside a model. And that's why I will talk about, and that's what we will evaluate. So just a brief talk about the philosophy of the making of the model. From the bottom to the top, you have different test samples. You know, the anatomy of the wood. Here we can see a tomography of wood is reconstructed. We have the dynamics of the quarters. We have, for example, the properties of a beam of wood of a sample. Then we increase the complexity of the model. And we had a bridge, we have a FO length, we have different parts that are spared. And after we have a sub-assembly. So we have put together the side, we have put together the box or the neck. Then after we have the almost full complex assembly, and after the complete structure. So this is how we create a model with different steps. Make different steps, like how we make a violin with different steps. And the model is the same way. But so when you have mastered each low-level elements to increase the model fidelity, if you do if you go back and from top to bottom, know that you have your full model. That here, a violin, for example, you can evaluate what is, for example, the influence of the eigenmodes of the quarter on the full model, because you have a way that exists between the full model and the quarters. So this is a way to use a method that we can use to say, well, on my model, considering the dynamics, the most important parameters are, and we can list the most important parameter and rank them. So the research objectives are to explore the potential of such models in low to medium frequency range. We do not consider very high frequency up to 4,000 Hertz, for example. And it's easy to develop physics-based model it's easy to develop a model with high geometric fidelity, but it's hard to model correct physics, quantify material variability, and account for Luthier's fine-tuning construction process. For example, just a small change on the olives of a bridge can have a strong impact on the sound at the end. So in the model, we have to be able to consider this kind of very small change. But it's a very high stake in a industrial domain, and more, well, it's very used. Now, if you want to make a plane, most of the first steps, you will not make a real plane and try it with different kind of wind, etc. You create a model of the plane. And you will check if with the model, the plane is okay. And after, if it's okay with the model, you will make the experimental part. So before the process of making the real part, a model can be very useful. And yeah, our objective is to provide instrument makers and curators decision support tools like models. This is the objective. And we'll see what are the current lockers and what we still have to do. So I will only focus on the instrument. So I will not talk about musician. I will not talk about bow, actuator, string, environment, and listener. So I will only all what I will say is about the instrument, and I will not talk about quality or sound or any things like that. I will talk about instrument, its geometry, its assembly, and its material. That's the only field. And in the vibratory domain, I will talk about I will consider on the models, the different part of the material, its rigidity, its density, and its damping. For the geometry, the shape of the instrument, the thickness of the plates, and also, of course, the model as arches, but it's not or neck reversal, but I will not change them. We will only change the thickness. And also presets, so in the model, we can change the position of the sound post, position of the bass bar, the shape of the bridge, etc. So this is the vibratory domain. So just a brief talk is when you use a model, it's very important to consider some things. That what is a proof? So how a model can be used as a proof, and how much a proof is a proof. So we have to consider statistics and be able to make a lot of computation. So we consider a lot of computation with another lot of computation. And we will check if we have a big difference between this is just a way, and this leads to a question: how to establish a limit between what is called a scientific approach and what are beliefs. And it's a very thin frontier, and we have sometimes to cut very roughly and to evaluate this is relevant or this is not relevant, with different kind of criterion that Karl Popper has developed. And we had different approaches. Deterministic approach means that we consider one parameter of the wood and we see what happens. And stochastic approaches means that, I don't know if you can see my camera, but yeah, we can, yes?
Yes.
Yes, you can hear my camera. So this is a small thing that there is a lot of teal balls here. And this, it's like if I was taking a wood sample. And what happens is that at the end, each wood sample is variable. I don't know what each wood sample will do, but at the end, it has some kind of curves. So stochastic means that I will not consider one ball, but I consider the shape that the ball are displayed here, as you can see. This is called, for example, a Gaussian or a bell curve. So instead of using one value, I implement probabilities of values. So when you, for example, for spruce has a density between 0.35 up to 0.5, and between 0.35 and 0.5, when you take a piece of wood, it mostly have a density like 0.41, 0.42. It's just the species, the wood species, it can be considered as a law this way. The same for the rigidity, the same for the damping of the wood. It's not one value, it's a lot of different values that are probabilistic. So that's what we consider. Yeah. So, and also there is a lot, sorry, it's in French, but there is a very important point is that we have to consider population, not one sample against one sample, but population. Because if for example, I want, you can see two graphs. On the left graph, I want to check what something like, for example, the eigenfrequencies of the first eigenfrequency of the B1 plus of a violin. So I have a different violin that are made in a way and different other violins that are made in the other way. And the red square and the blue dot, they are two different measures. Then I consider yes, the measures are close because it's close on my graph. But if I see the populations, well, with all the different samples, they are not the same. So we have to consider population and not samples. So we have to consider a lot of measurements and a lot of samples to be sure that we are not misled by the fact that our first measure is okay. And the same way, if you see on the right, the population are the same, which means that, for example, you have made a change on an instrument, and you want to see that what was the impact of this change, and you compare instruments in a nominal state and instrument with this change, and you compare the population. The population can be orthogonal or they can be the same. So this is very important to consider the population. So that's what, just a very brief point about it. And this is why models are very useful, because in reality, it will be very hard to have enough instruments. And this needs very, very dedicated studies, but usually a maker doesn't have the time or to make, for example, 15 instruments of kind or 15 of another kind and to compare them. It's very hard. So the idea of the model is to be able to have these 15 instruments, because it's only computation time. It's like 30 minutes to test a new instrument, to test a new design. I will show you after some tools that we're developing. So some generalities of the wood. I told that in the model, the variability was very important to be taken into account. And the tone wood, so the spruce and maple wood characterization is necessary. So Eric Bremo will talk about wood later during this conference. So I will not detail this very much, but just some key elements. So we need reliable properties of wood for numerical models. We have to know the knowledge of the variability of spruce. So what is the shape of the distribution of the values of spruce, for example? And we will use a non-destructive method and a vibration-based method. So the wood is very variable due to many features. For example, the texture, which means that depending on the early wood and late wood that you have, the properties will be different at this very small scale. And the wood, the xylem, which is the part you use for the instrument, it's a skeleton, it's a muscle, it's a vascular system, it's a respiratory system for the tree. So depending on what the tree needs, the wood wood cells just under the bark will be created with different shapes and different characteristics, depending on what the tree needs at this moment, for this precise moment. So some mechanical definition of wood. The wood has a density. It's the ratio between the mass and the volume. It has 3 Young's moduli that, from an orthotropic point of view, it's the stiffness in this direction, longitudinal direction, tangential direction, and radial direction. Most of the time, for example, for a slab cut, you will be in the longitudinal tangential direction, and quarter sawn, you are in the longitudinal and radial plane, direction and plane for a quarter sawn wood. So depending on how you have a quarter that is slab cut or quarter sawn, etc., you will have different properties. And this property depends on how the wood is, how the wood cells are ordered in the instruments. There is also shear properties, which means that when you are trying to bend and twist, when you are trying to twist the wood, you have some stiffness, so the bending stiffness and the twist stiffness, which are not the same. Then there is the variability between species, inside the species, between trees, and inside the trees. And sometimes you may have more you may have more differences inside the same tree, depending on what is the age of the quarter that you have taken and around the circumference of the wood than with another tree. So you can have quarters that are closer to another tree than inside the same tree. And also for the species, you can have, for example, a wood that has properties that are closer to another species. For example, you have a sample of maple that can have equivalent properties, mechanical properties, than another species rather than another tree of the same species. Because I will show, well, if you can see again my cam. If this is my first wood, so can you see the paper that I'm showing? Yeah. Yeah, it works. Yeah. So we have for example, the first species. So we will take, for example, 15 parts of a wood. So we have this kind of distribution. Okay. And if I take another wood, I will have another distribution. It's the blue one this time. So as you can see, the population are different, but there is a part where they are crossing. So the properties are the same, depending whether with different species. So it's possible with different species to have the same properties, because the wood is very, very variable. And also, it's very variable, but also it's sensitive to humidity, so it evolves also. Just a brief talk on the tracheic properties. Each wood cells of spruce, it's called a tracheid, has different walls and different layers. And the three polymers that constituents of the wood, cellulose, hemicellulose, and lignin, are not distributed in the same way in the different walls. Which means that, for example, the cellulose, which is very stiff, the cellulose is stiffer than the crystalline cellulose is stiffer than aluminum, for example. It's ordered in the different ways inside a cell, so the properties of the cell is not the same. And you have another wood cell, and another, and another, and another. And at the end, you have the global behavior. Depending of how each wood cell is ordered in the instrument and how each wood cell is made with the different constituents. So this is very variable. Also, I talk about the hygroscopicity of wood, which means that when you no matter how the wood has been, how much time the wood has been dried, when you have relative humidity changes in the air, the wood absorbs or release water. And you usually, like at 50% humidity, the wood has 10% of water, which means that on a 100 grams plate, at 10% humidity, you have 10 grams of water in the wood, which is its equilibrium moisture content. And when the wood in the water in the wood changes, for example, if you increase by 6% humidity in the air, from 50% to 56%, you will have generally plus 1% of water in the wood, but which means that you will have your density that will increase and your stiffness that will decrease. And 1% in the wood of water means 3% less nearly of stiffness in the wood. So at the equilibrium. So between 25% relative humidity and 75 or 85%, you have a very wide span of changes of humidity, but also of changes in moisture content of wood, which means that you may have cracks, you may have also the strains, you may have creep behavior, and the sound will change because the frequency, the resonance frequencies depend on the geometry and depend on the material properties. And the resonance frequencies, if the mass is increased and the stiffness is reduced, the eigenfrequencies will be lowered. So when the relative humidity increases in the air, the eigenfrequencies diminish. So they are never fixed, they're never the same value. So this was just to talk about the wood. So we have studied a lot of samples made of spruce and maple that we can see for the guitar furnitures or quarter wood. And you have tested them with laser vibrometry, which consists in measuring the displacement field of the plate. There you can see when the frequency increases, that there are different peaks. So you have seen this earlier. And these different peaks are the different twist and bending modes of the wood. And they are getting more and more complex when the frequency increases. Okay, and there is 3 modes that are very important, like the first longitudinal bending mode, when the wood is like this. The second, when the plate or the quarter is having this motion, and another one when it's twisting. And with these 3 modes, it's possible to evaluate the stiffness of the wood. So later I will show you how to measure it with less than 1 euro sensor. It's possible to measure the frequency of these different modes, and with the frequency of this different mode, you can evaluate the properties of wood in a workshop. And yeah, so we have measured a lot of. This is a method that has been proposed by Jim Woodhouse in 1987, by the way, with McIntyre. And also Moline, different method to evaluate the properties of complex shaped material. So when we have measured a lot of samples, we have observed the material properties as a function of the quality. So what is the graph? We have the specific modulus, which means the stiffness divided by the density on this part, for example, the upper left part. And première, seconde, troisième, and quatrième in first, second, third, and fourth quality. Quality as sold by the seller, the wood seller. And we have different values. And what we can see is that we do not have a specific value, but you have a different box and whisker plots, that's what it's called, with a median, which is the red line. And between the upper and lower part of the blue box, you have we have between 25 and 75% of the samples. So which means that more than half of the samples are comprised inside the box, the blue box, as you can see. But there is a very interesting thing that we can observe here, that is that the second, third, and fourth quality can have the same properties than the first quality, because it's very variable. And also, another feature is, for example, if you see the center bottom graph, for example, the twist stiffness increases when the quality is getting worse, because first is the better quality premiere. So when the quality is getting worse, so when the price diminishes, for example, the stiffness in twisting increases. This is yeah, this is quite clear, and that's
Romain,
yeah.
Romain, you should explain what are the different graphs, I think, for people.
Yeah. Okay, sorry. So each graph displays the results. L/ρ, which is the density, means the stiffness divided by the density. And the value of the stiffness divided by the density is important in dynamics. So each graph displays the stiff. For example, this one, you can see my mouse? Yeah. So this one is the stiffness in the direction of the fibers of the grain divided by the density. So we can see an overlap of the properties. this is the damping divided by the density of the wood in the longitudinal direction. So this is the properties of the wood, which increase when the quality gets worse. So this is first quality, second quality, third quality, fourth quality. So the highest price is on the left part of each graph. And you can see that the damping increases when the quality diminishes, which is maybe interesting or maybe what is expected, I don't know. This is the damping in the radial direction, which it's so in the other direction of wood, in the cross grain direction. And so this is graphs that are used to show that, in fact, when you consider different qualities in terms of density and mechanical properties, there is a very big overlap. So mechanically, different qualities are not necessarily very different mechanically. So that was the idea I wanted to talk. It has been
Romain, there is a question now asking about the radiation ratio.
Yeah, the radiation ratio is when it's a parameter that is used. So there is different kind of criteria that you can use, like specific modulus, specific rigidity, which means stiffness divided by density. You can also use different kind of features like acoustic conversion efficiency or radiation ratio, which are the different way to calculate this. But yeah, problem is that I don't have the correct equation, but it's a mix between damping, stiffness, and density. And so there is different indicators that you can use when, yeah, I could have displayed radiation ratio or acoustic conversion efficiency. I'm not using it because I'm not dealing here with sound or radiation, and I'm only dealing with dynamics. So dealing with dynamics means that I'm only dealing with the specific modulus and not the radiation ratio. I take care, I do not use a lot radiation ratio and acoustic conversion efficiency because this can be misleading. Because usually there is a lot of beliefs that a high radiation ratio is better for the sound, or a high longitudinal stiffness divided with a very low density and low damping is better for an instrument. But it has never been, maybe I'm mistaken, but it has never been proved. And so I'm not dealing with that kind of parameters, but maybe I'm mistaken.
Okay, so, and another question is like, did you compare different sellers, or all these wood that you're talking about here are from the same source?
They are from the same seller, but Iris will discuss about different sellers. Okay. And probably it seems that we have the same results. Well, this is just to talk about the very big variability of wood, and wood is very variable, and even if we consider a quality or another, you have very, very wide span. And so it's very variable, but I will show you the good news is that the choice of the makers are very important, and which reaches the variability of the wood. Yeah, so with these different data, we have considered, we have created different laws. They are not very accurate for this one, but the idea is to implement in models laws instead of unique values of wood. So different applications. So I will consider, because I'm talking with violin makers or quartet instrument makers, violin. So this is the model of a violin. With the model, as you can see, you can see the fingerboard mode, or a mode that deals with the head and the soundboard of the instrument. We can also evaluate the displacement of the sound post, the effect of the displacement of the sound post on the bridge motion and on the different parameters. The objective is to associate instrument maker choices and dynamical features. So if at a given step you choose to reduce by 1/10 of a millimeter the thickness of the plate. What does it mean in terms of eigenfrequencies, for example? So the model has been created with templates, and it's a parametric model. So in the model, you can change each thing you want. It's a quite realistic model, as much as it's possible, but it's never perfect. So this is the computer-aided design of the violin. Inside, you can see everything. You can see the lining, the ribs, the sound post, the bass bar, the bridge. There is a tailpiece, there is a chin raise, there is a saddle, bottom saddle, there is a top goblet saddle, etc., etc. And also we compute the acoustic cavity of the model, which is the air inside the instrument. We also consider the orientation of the side to be sure that they are in the correct orientation, because they are bent. And we have a finite element model for this purpose, which is a mesh. When we have drawn the instrument, we put some physics inside. And the way to put physics inside is to put some what is called a mesh. And a mesh will be a way to perform computation. If you don't have mesh, you cannot make computation on a computer. So we have considered the model analysis. Yeah.
What is the arching model did you use? Or?
For the template, all templates, but not. Maurice Fauconnier is not famous, but for the demonstration, it didn't matter. It was just a demonstration.
Okay.
Just yeah, template for all the instruments of the early 20s, but yeah, I should consider to see the chat, but I don't know where it is.
It's okay, I'll.
Yeah, okay, you can tell me the different questions. Okay, right. So this is the model, and all models are false. George Box said it in 1976, that all models are false, but some may be useful. So the idea is not at all to have the most accurate model possible. The idea is to have a parameterized model, and on this model, I can change everything step by step, which is impossible in reality. So I consider the material directions. So the wood is orientated in different directions. And also the mechanical parameters. So a parameter of wood for each part, densities, stiffness, I said. And also I've implemented the wood properties. So I have an average of the properties of wood. So as you can see, for example, the stiffness of the wood, of wood selected for instrument making. It's not all the spruce. It's already selected for instrument making. So it's not the selected wood, but it can have values that range from a factor by 2. It can be 0.9, it's not GPA. It can be 9 GPA up to 18 GPA. So the values can be multiplied by 2 when you are choosing, when you have wood that are already used for instrument making. In the same way, in the other direction, for example, there is the radial direction. It can be multiplied up to 3. So you can have a value that is equal, for example, to 600 megapascal, it's a unit, and it can go up to 1,800 megapascal. So this is very, very wide span of material properties that we consider, which are very close to the usual reference values, for example, that you can find in Iris Bremo's work in 2011. So we have a model and we have wood properties. Now I will talk about a new thing that we might have not seen that. So I will explain. We are using a hammer that creates an impact on the bridge. Like there is on the left part, it's a hammer. And yeah, there is a mistake. The total duration is 1 millisecond. It's not 1 second, it's 1 millisecond. And you have a hammer that is on the side of the bridge. And we observe the wave propagation on the wood. So what is red is when the wave is up in the up direction, and what is blue is when the wave is in the other direction of the reference frame. So as you can see, when you have an impact on the side of a bridge, you have a wave that propagates upward in the up direction on the left part and the bottom direction on the right part. But what you can see is that the wave does not follow the shape of the bus bar. And the duration between the moment that you impact the bridge and the moment the wave arrives on the, for example, in the upper and lower part, it happens less than 1 millisecond, 1/1000th of a second. So this is not a transitory at all. This is not what we call transitory, but it's just the propagation of the sound. And as you can see, when it goes up to the lower and upper part of the plate, here and here, after it's like a very big mess. There is a lot of things. Well, this is in time that happens, but in frequency domain, we can see what is called the resonant modes of the violin. So the apparent mess drives to modes of the violin. So this is the top part, and on the back part, you can see that the vibration happens in the sound post at first. So when there is an impact on the bridge, you can see the wave propagates inside the sound post, and after it arrives at what we see on the right part. There is a big motion, which is the wave that arrives from the sound post. So this is just a way to think in the time domain. This is the time domain. The wave propagates. But when I will use a picture that had been proposed by Colin Goff in 2000 that I've used, and which was pretty cool picture. So I'm creating an adaptation. So when a string excites the violin, it touches the bridge. The string has some harmonics, because when you have the fundamental and different harmonics of a string, which are the multiple of the fundamental frequency. When you have a bridge, the bridge has some resonant frequencies. As you can see, there is a peak of the bridge alone. It's the moment when the peak is having a motion in its plane, and the bridge is on a real instrument. So what was at the beginning only a bridge with only one peak becomes a bridge with becomes a full instrument with a lot of resonances and anti-resonances, and also a peak which is due to the bridge motion. Then after, the first harmonics of the string that was very high for the fundamental and decreasing, well, they are modified because there is a dynamics of the instrument. And what we are using is, instead of using real admittance measured on the real bridge, what you see is computed. So we compute the dynamics of the bridge, the dynamics, the vibrations, behavior of the body. Then we have a full admittance of a model. So now the question is, what has an impact in terms of material or geometry on what is in the model? So just a brief talk about the bridge. Well, when you have a bridge in this way, it has a main resonance that we at like 3000 hertz when it's only alone and clumped on its feet. And when it's on the instrument, you can find what is currently usually at more than 3000 hertz at like 2600 hertz. But this component. It's what Jim Woodhouse called the bridge hill years ago. So we can see different kind of movement of the bridge. And also what is interesting is that when you have a blank from Despio or Aubert of the bridge, opening the different parts will reduce and will modify the eigenfrequencies of the bridge alone. And also when the bridge is on the instrument, you can see the different motion of the bridge. All right. Yeah. So with the model, we can also compute the tailpiece modes. So all the tailpiece is vibrating, twisting inside the instrument. We can also compute the fingerbore mode. Can also see the vibrational modes below 800 Hz that are very canonical, B1 minus, B1 plus, C4, CBR mode. So these are different computation. We can also compute the Helmholtz mode, which is the mode of the cavity inside the instrument, which is about 300 Hz on the simulation. But NIA in 2015 showed that when we are considering the fact that the cavity is flexible, it's from 300, you go back to 280, which is the usual value that is measured on the violins. But you have different kind of acoustic modes. And we also can compute the stress, which means that when you strain the matter, it has a stress which leads to cracks. So we can see that stress produced by the bar, the stress produced by the sound post if the sound post is too long, and the stress and the displacement produced by the strings when the strings are pulling the instrument. So I will show you some results. We are considering different parameters input, like geometry, material, etc. And now what we can see is that we can rank on the eigenfrequencies what is the most important influential parameters in terms of wood parameters or moisture content. Sorry, it's in French, but the shear, the twist modulus of the soundboard is very important. In fact, on the eigenfrequencies, considering the model that is used. The density of the soundboard is important. The density of the neck, because we have considered all the different modes, and so it has an impact. But we can rank what are the most important wood parameters on the eigenfrequencies. I'm not saying it has an impact on the sound or it has an impact on how a musician will like the instruments. I'm just saying, using this model, what has an impact on the vibrations of the violin. And when we are gathering all the results, the design, like several tenths of millimeters of the soundboard, and what is the usual choice of a maker has more impact than the full variability of the wood. And also the preset has a non-negligible impact, like position of the sound post, the position of the bass bar, the way the bridge is cut, etc. On the bridge admittance has a very strong impact and more than wood. When you consider the design and the preset, it has more impact than the full variability of wood. And I'm not talking about very, very big change, a very big instrument. It's only several tenths of millimeters in the thickness of the plate. It's only the F-hole shapes, etc. So this is,
Romain,
yeah.
Romain, there is a question about how you compute the sensitivity. If you can address this fast, you do it, otherwise you can do it at the end.
If what?
There is a question about how you compute the sensitivity.
The sensitivity is computed with a method that is called the Morris method. We are making a lot of computation, like hundreds of computation. And each time we change one parameter. We change one parameter of wood or one parameter of geometry, and you observe the difference on the eigenfrequencies. Then we change another parameter, we observe the difference, etc., etc., etc. At the end, we check what has the most changes the frequencies or the bridge admittance. Yeah.
But you only did it on the mode frequencies.
Sorry?
You only did it on the mode frequencies. You didn't do it on the
bridge admittance also. The bridge admittance shape and the bridge admittance maximum value. Okay. Like the bridge hill maximum value, as you can see. I've also computed it on the, but there is, yeah, it's in my PhD thesis. I can share it, but yeah, it was a bit too technical. But yeah, I've also evaluated what was the influential parameters on this part of the violin, the bridge hill. So the sensitivity has been computed using Morris method and a numerical model. and but everything can be found in my PhD thesis that is available on ResearchGate. And so there is a lot of input parameters, and there is a lot of features like frequencies, like bridge admittance, and we make a link. We try to create a link between each one of these features. So as you can see, for example, climate, which means that the moisture content evolution of the wood due to relative humidity change has a non-negligible impact on the dynamics of the instrument, even when it's finished, when you are at the equilibrium moisture content.
There was one question about how can a violin maker can simply calculate the stiffness? Is a Young modulus?
Sorry, which question?
Is like how can a violin maker can simply calculate the stiffness?
I will show you.
The Young modulus.
I will show you. There is a, yeah. I have prepared a lot of stuff just around. So whenever I finish this talk, I will show you different methods. Like for example, a 3D scanner. Yeah, I will show you that this part. So yeah, I will continue. So using this model, we have considered one thing. How can the model be used? What can be used to do? Because it's very, experimentally, it's very hard to make the link between what I've chosen when I was making an instrument and at the end it sounds. But the model can have very interesting outputs when you are, for example, dealing with the, before making a wood modification, is this modification important? And will the wood modification be measurable? So that's the object of this application. The wood treatments are very common and they are performed by musical instruments. There is a lot of tradition and secret and also different kind of folklore around all the preparation of the wood. And there is also researchers that propose polymers, fungus, or heat treatment to modify the wood properties. But the effect of wood modification on violin dynamics or even the sound, they are yet to be studied, assessed, or discussed. So I have used a model with different references of wood modification, as you can see for spruce, maple, spruce, it's a lot of spruce. And also the fact that the spruce has indented rings. It's a Birklow wood, hazelfish, it has a lot of names. And also we can see for each treatment, the difference in terms of density, longitudinal stiffness, radial stiffness, damping, specific modulus, etc. So the idea is, okay, we modify wood, we observe that it has an impact on density, for example. So probably it will have an impact on the properties of on the dynamics of the wood. But when we have to put it into context, yeah, this was just to talk about the Birklow spruce, indented rings. It's a typical spruce that has rings that are not usual, and it can be very, very stiff in radial direction. So the instrument maker precision is nearly 0.1 millimeters when you are making the thickness, for example, with a thickness caliper. The relative humidity can range from 25 to 75%. The wood properties of all the parts, they're unknown, they're uncertain. They are following variability and probabilistic definition rules. So, and also when you make an instrument, you can have variation in terms of F-hole length, F-hole width, bass bar length, bass bar position, bass bar rate, bass bar height, soundboard average thickness, soundboard back average thickness, etc. So all this can vary, and you cannot be more precise than the minimum measurement tolerance of your measurement device. You cannot be more precise than a thickness caliper when you are measuring with a thickness caliper. So what is the impact of wood modification when in fact there is a lot of parameters that are uncertain? So we have made a lot of computation, once again, with a lot of standard deviation. So which means that what is the relative standard deviation? Like for example, I will take the value irreducible uncertainty, 3.1 RSD. It means that when you see the frequencies of an instrument, due to the fact that the wood is variable and the fact that there is change in relative humidity and your making tolerances, you will have 2/3 of your frequencies that will be at plus or minus 3%. It's impossible to be more precise when you're making an instrument, and it's an ideal case, because in the reality, the gluing stiffness, the different amount of glue that is put, the different variation is not taken into account in the model. So in an idealistic way, when you add geometric tolerances, material variability, and irreducible uncertainties, you have like 3%. Most of your frequency resonance, for example, can be at plus or minus 3%, which means like if you are at 1000 Hertz, can be at 1030 Hertz, 1000 Hertz can be at like 1030 Hertz or 970 Hertz with the same probability. It's impossible to be more precise, even with a very, very perfect model that has not losses, that has a very good clamping condition, which is not the case in reality. So in reality, it will probably be worse. So what does it mean? It means that when you will check the admittance of a violin, you will have what you can see in black behind. It's kind of noise. It's the noise of the, for example, if you measure bridge admittance with a given design, even with the best making possibilities, you will have some noise because there are uncertainties that will imply that your bridge admittance can vary in frequency and in amplitude. So the question was, will the wood modification be observable inside this black noise? This the fact that bridge admittance can vary a lot. And we have seen that most of the modification cannot be seen just with the dynamics of the instruments. Yeah. So yeah, there is a question, but I will answer later. So what it means that effects of treatments on specific rigidity must outreach a threshold to be reliably measured. But it's a threshold that, for example, if you change by 20% the density of the wood, I have no idea what is the state of the wood at this moment. But it's probably not very usable and not very carvable again. So this is not in order to say, no, okay, if a maker wants to or likes to trade the wood, it's fine, it's very cool, it's very good. But it cannot be, it's very hard. I would just say that using this model, we have proven that it's very hard to establish a link between sonority or dynamics and the treatment of the wood. Which doesn't mean you don't have to do that. Not the same thing. So yeah, so this is an application on the treatment of wood. And so we have made another model of a cello. Pietro Guarneri cello 1734, which is in the Cité de la Musique in Philharmonie de Paris in France. And we have computed on this cello, because this cello has a worm hole in the back that you can see here on the model. And we have created a very detailed geometry in order to compute the strains and the stress of the cello. So when the strings are stretched on the instrument, we have observed what was the impact of the strings on the instrument, because the question was that there is a wormhole in the back of the instrument. Should we put again strings or not? Or is the wormhole that you can see here is a problem when you want to put strings again? So we have computed the stress in the instruments. We have the different stress components, and we can see here at the wormhole the different stress field. And we have observed that there is a safety factor of 20. So the string should be 20 times more straight to imply that the cracks would propagate. Which, if you stretch the string 20 times more, the string breaks, and there is other parts that are broken before the crack propagates. So this is another criterion that can be used for curators to consider this instrument can be used or not, and you are mixing the expert, the instrument maker point of view with a more like engineer's point of view. All right, so yeah, and this is very useful because you can see the different parts where the instrument has a risk to crack, like for example near the fall length, under the bridge, behind the sound post on the back, near the heel, near the bottom heel, near the neck. Well, if you are working on old instruments, old cello, I think that's where you often see cracks, in my opinion. So, and you will also compute the eigenmodes of the cello. So if you have questions or if you want to make comparison between violin and cello, we can use the model of the cello to evaluate the different modes and evaluate the same thing. For example, what is the most important parameter on the mode? Terry asked me, did I perform this measurement with or without the strings tuned to normal pitches? Yeah, we have made measurements. So this is not a measurement, this is a computation, the string here. But I've made measurements on the violin again frequencies, for example, with a laser vibrometer. And there is a strange result about the string effect on the violin, is that, as you can see, there is strains that are due to the string when the strings are on the instrument. But when we measure the dynamics, which means the eigen frequencies of the violin, with the normal pitch of the strings and with the strings an octave lower, the dynamical behavior is the same for the guitars and for the violins and for the viola. That's the three instruments I have tested in this way, which means that the pre-stress field of the strings, it seems, don't change the dynamical behavior of the instrument, which is actually counterintuitive. But that's a fact, that's a measurement. So yeah, we might have a talk about it, but it's very strange for me to observe that. So the strings change the static behavior. It can make a collapse, it can create cracks. But when you are changing, for example, the angle of the neck, the tension of the string changes. But it seems that it doesn't change the dynamics of the instrument.
So you mean the dynamic of the instrument does not change? You mean the modal frequency does not change?
The mode shapes and eigen frequency do not change, except the one of the tailpiece, of course, the first one.
Okay, that's a bit surprising, actually.
Yeah, that's very surprising, yeah, of course. That's very, very surprising. But that's what we measure on guitar, viola, and violins.
Okay. And when you do the modeling, do you put the stress of the material? Like when you put a string on the instrument, there's a stress on the structure. So do you put a stretch of the structure in consideration when you do the modeling?
That's what you see. This is a model. So there's the stress of the instrument due to the strings when the strings are stretched.
Oh, okay, I see. Yeah.
This is a computation of the stress field.
Okay.
I don't know if I answered the question.
Sure, yeah, go ahead, thanks.
And so we can compute the stress, the static behavior, and the dynamical behavior, the eigenmodes of the cello, the eigenmode of the bridge of the cello, etc. So I'm getting to the end of this part of the talk. And so we have proposed numerical tools. For example, you can see on the right part a small video where you can change the soundboard parameters like the bass bar length, height, the shape of the F-holes, the thickness, the arch of the soundboard, and at the end you can see what are the different eigen frequencies with different kind of modification. So it takes 5 minutes on a regular computer to compute this. To compute, for example, well, we have seen it very briefly, the fifth modes or the n-first mode of the free plate. So we can compute the eigenmodes, the boundary conditions, but currently it's made with very costly licenses, and I'm quite optimistic that in a couple of years we'll be able to have changed every licenses with free softwares or open source softwares. Yeah, what was the thing? So yeah, we want to change. We want to go to free softwares, because this way we'll be able to propose it to everybody. And I will show you a free software that I can use to, if you want to the model and the results of the model, I can share it with you, and you will be able to see each mod with a free software and the computation that has already been done. So the perspective is to open source softwares, complete structures, variability, etc. We have also, yes, but we can try, for example, if an instrument maker wants to reduce a wall, for example, an instrument maker asked me, well, how to reduce a wall for an instrument. So the idea was to put some stiffeners. Dennis Brown, I will send you the presentation if you want to see the bridge trace image. Okay, no problem. I will send the presentation. So this is an idea of a wall reducer, for example. The idea is to test it. We can, with the model, it's almost it doesn't take much time, it doesn't take much money to test it. So this is just a proposition to evaluate different states. It doesn't mean that this will be the accurate sound or the accurate the real behavior, but you compare states with the model and the equivalent states. So models are false, but maybe useful. And there is still ongoing research to provide musical numerical tools. The material properties are now pretty well known, like density, stiffness, and damping, by the works of Iris Bremo also. So we want to mix my works with Iris Bremo's one to have the most material properties as possible. And the numerical models can be used to screen material properties and design effects. And we want to transfer these numerical tools to instrument maker, open source license, etc. So now I'm working at the ITEMM in France, and I will show you some current activities that we have. So I will show you very briefly what we can do. So if it's fine, because the idea was to show some very pragmatic things. So we go back to my video. I think it works. Can you confirm, Claudia, please?
Yeah.
Yeah, okay. So I can remove my mask because my colleague has left also. So I don't know if any one of you know what this is. This is a Xbox 360 Kinect. This is for video games at the beginning. But this can be used as a laser, as a 3D scanner. And I will just show you very briefly an application. There is a software that is called Scannect, which works with this. So this is like, this is very affordable. It's very cheap. So on the right side, so you have seen this. You have seen this part. This is just a violin body. I will show once again my second screen. So you can see the software. And on the software, I will say, I want to measure something that is like 50 by 50 by 50. And let's start. Okay. No, it would be better if I plug this here. Sorry. I go back. Yeah, no, it's plugged, okay. This is just in order to show you some methods that can be used for very practical measurements in workshop. So once again, you can see the interface of the application. So there is a video here. This is a video. This is on the right part, the distance. And if I do this, I click on OK. So we are making some tutorials for everyone to be able to measure with a 3D scanner, for example, violin plates, etc. So this is quite, oh, I've been too fast, okay, again. Okay, so very briefly, so I finished my scan. So now it's creating the frames and it's finalizing the mesh. It's almost done. So now I have what I have measured, which needs to be refined, of course. But I have measured like during 10 seconds maybe. We can see the different position of the Kinect of my camera. And so I have the beginning of an idea of, yeah, the resolution is a good question. We are finding, we're trying to test if it's like 1/10 of a millimeter. So this is what we are considering right now. It depends on the light. It depends on the time you use to make the measure, or the duration of the measurement. It depends on a lot of parameters. But it's the way, for example, to when you have an instrument that is inside your workshop, or you can just scan it and you have a numerical copy. And with this numerical copy, you can very easily after create, for example, when you are making a sound post patch, you can create the opposite part for the sound post patch when you want to glue it with a 3D printer, for example. So this is just, yeah. The aim is to reach 0.1 millimeter. That is the aim. We are evaluating if it's or not 0.1 millimeter. Yeah, your Xbox will be reborn, King Leo, of course. Yeah, that's right. It works pretty well, in fact, and it's yeah, it's very. And it's like 10 euros or 20 euros, this kind of device, because that's the mass production. So it's kind of very affordable 3D scanner that you can export it in a software. You can export it wherever you want. You can print it. You can use a 3D printer. You can create the different molds around an instrument that just dropped, etc. So this is one of our topics is to currently, and we can discuss about it later, is to develop a certain number of tools that are very pragmatic and very easy to transfer to workshop. So a second part is it's called Pinastran. So Pinastran is a free software that has been developed by yeah, I don't have the name here. Yeah, it's been developed by Steve Doyle, and this is a software that is free, and you can download it, and I can send you the different data you want on the cello. For example, if you want to see the cello modes, there is no problem. I can send you if you want. So you can see, you can open my results, and you can see the different modes on the violin just by downloading this part. So you can see as a function of the frequency. The different modes, which not mean it will be exactly the same frequency, but it's kind of you can see the eigenmode shapes and the eigenmode frequencies. For example, the fingerboard mode at 665. It's called Pinastran, and if you're interested, I can send you my models and the software if you want, because it's free. So yeah, well, this way you can animate, you can see the shape of the different modes on the violin. Yeah, for example, there is another mode where you can see that it's moving. So this is another application. We have also made guides for the disinfection and cleaning of the instruments, and trying to, because it was a very big project we had for the stores that would reopen, and for the repetition and for the test of musical instruments. What are the ways to disinfect safely for the instrument, etc. An instrument. So there is an English guide for the bowed string instruments that you can see right now on the website of the ITEMM or CSFI. And then you can see the different compatibility between materials and the different disinfection products that are known currently. So this is for bowed string instruments especially. So if there is a conservatory or a school or a musician that asks what can I use, or what should I not use to, for example, alcohol is very effective, but it's very not good for instrument. So this can be used for this purpose. So it works pretty well. So we are, you can download it on our website, the disinfection guide for all the families of instruments for your customers. So this is the end. Thank you for your attention. And yeah, I'll switch again the camera. and we can some question, and I can show you, for example, different part. If you how to determine the modulus of wood with a wood blank, or the 3D printing we made. For example, we are making some tools for violins, because when you are making when you are gluing a violin neck, you need some rolls, but it's not very easy with 2 rolls with an unglued fingerboard. So we are printing with 3D printers, dedicated tool with, for example, you can evaluate at 27 millimeters the projection of the fingerboard at the end of the instrument, and you can measure very easily. For example, with this kind of device, you put inside the roll, and you can measure the projection. Yeah. You can measure the different parts of the instrument, and we propose the plans of this kind of tool, which is very light, so there is no risk of breaking the soundboard with it. It's very light, it's very cheap, but it's very straight, so it's very, you can use it quite accurately to evaluate the reverse of the neck, or the reversal of the neck, and also when you are gluing it, you can have an indication when you are making the bottom, the top heel, the carving. So the different parts with 3D printers, and we're also making composite materials for instrument making. So this is a soundboard, guitar soundboard. Because there is, we want the companies, manufacturers to use composite instead of bulk wood for instruments. So this is not wood, this is a composite that we make with natural fibers, but it looks like wood. Also, I make, I have not cut it with laser, but I can make in 30 minutes a back of a violin. Or the most funny part, a piano soundboard, it takes 2 hours to make the long tenor soundboard with the different methods. So at the ITEMM, we are working in the different fields, and we are working for the instrument makers. So if you want to have some collaboration of some work, it's fine, and we can talk, and we really want to share the knowledge, and we really want to share the different tools. Yeah. What other we are? Well, we are the 3D printer. We are printing a tool for guitars, for example. We have just printed it. So it's for our students. For our students, we are making different kind of tools. So when they are testing new way, this is for guitar making. This is for woodwind instrument making. This is for flute, for example. This is in order to test for piano presets. So we are, for our students, we are printing, and also for makers, we are printing different kind of tools. So our aim is really to share it with makers, and free softwares, and open source softwares, and free tools. Okay, so there are both models, of course, online. Yeah. So there is still 20 minutes, but I think we can have a discussion about, yeah. Claudia, you are muted? Yeah, that's fine.
You were supposed to talk about how to measure stiffness.
Yeah, I will show you. So, I will show you something. Maybe I should have used the Xbox. It was a better camera than this one. Okay, so very briefly, how can you measure stiffness? I got a computer here. I got a piece of wood. It's for the guitar. It's okay with the image? It works very well. You can see very well the image. Okay.
No, and we don't hear you very well.
Oh, okay. So I try to speak. Okay. So I will speak here. So because it's an actual real-time experiment, so of course it will not work like all the experiments when they are tested in real time. So there is a software that is called Sonic Visualizer. I will show you Sonic Visualizer. But I'm using another computer because I was not very confident in the fact that using this computer with a specific tool, it would work. What is Sonic Visualizer? I will show you here. So this is a free software that is very, very useful because it can be used, for example, I can record the sound. So if okay, and so you can see that it has recorded something, but I can perform very easily. I can evaluate the spectrogram with this software, and I can send in this spectrogram. I can see, for example, the different parts. There is some signal processing, but it's very easy to use. And so this way, I can evaluate, for example, when I've been whistling. Sorry for the sound. Okay, so this was when I was whistling, for example, the sound. And I can evaluate, for example, the frequency of the whistling. So this is a software that is called Sonic Visualizer. So this is, for example, the whistling. So the idea is to combine this kind of software. So this was with the tuning pitch. As you can see, it's very straight, more than my whistling. And you can evaluate the frequency of this tuning pitch. So as you can see, I've just opened it and whistle and recorded. There is nothing else to do. It's very, very easy to use. And after, of course, there is some signal processing, but it's just in order to evaluate correctly a frequency. So my tuning fork it seems that it's quite accurate.
How do you read the frequency? Where do you read it?
Yeah, it's on the upper. The problem is that it's here. You can see on the upper right part here.
Okay.
There, this is the frequency, and as you can see, it's
440. Okay.
Yeah, voilà. Yeah, that's right. So you can see the frequency, but there is also a funny thing that you can evaluate. So if you put an MP3 in, you can evaluate the chords of the instrument of a sound. So it's easy to chord the harmony. You can evaluate also you can have a lot of signal processing, like for example the trying to find the fundamental frequencies. So yeah, as you can see, it has observed the fundamental frequencies at the moment. But it was not a very good sound, so it was well. All right, so this is a lot of different things that you can do. Yeah, I can also show the FFT of the sound. So the spectrum. Here we can see the spectrum, and when the tuning fork was working, you can see that there is a very big peak at 440, which is yeah. So yeah, this was my whistling. So I can, yeah, it's very, very easy to use. So I have put it on another computer, and I will show you with a simple measurement device. Some of you may know this kind of device. It's a piezo. Colin, I think you know that. You know this very well. So we are using this device with a card. So it's a card that is used to record a mic or a line. And you are using this card with the software that I'll show you. And so when I create an impact on the structure, for example, with my pitchfork, okay, I can record. I can record the impact, and so this has recorded. I have recorded the impact in vibration, not with a pickup. So I get the vibration.
So did you glue the piezo? Did you stick the piezo?
It's just with double-sided tape. It's very simple and very robust. And so not that much robust anymore. No, so I get this is my signal. And with my signal, I will perform the same thing that I showed you on the sonic visualizer, and I can obtain the three first frequencies. So the three first line of the on the dynamics. So I should transfer it, but it's not very easy. So when I have these three frequencies, what can I do with that? There is a lot of analytical models that we have used. So you have not my direction.
So you are measuring the first three modes?
Yeah, the first three modes. The first three modes that you have shown on the previous talk. And so you have the modes of the plate, and you have the twisting mode, bending modes, and radial modes. So when it's push, they are appearing in a given order, and it's very highly unprobabilistic that they are not in the right order, because Proust is as a given definition. So it's kind of Bayesian inference, but we infer that the frequencies will be in a given order. But what we do after that, I will share my screen. I propose, it's based on the George Woodhouse and Moline method. That you, on this, it's online. It's a computer, it's a calculator online, and you have to use this calculator online. You just specify the width, the length, the thickness of the plate and its mass. You give the frequencies that you have measured, and then after you get the longitudinal, radial, and shear stiffness, and the specific equivalent stiffness, and the anisotropy component. So this is how to simply evaluate the stiffness of a sample. Right?
Very good.
Thanks. And this costs like 20, 30 euros less, probably less. So it's a thing that you can do with your own computer. So there was a 3D scanning, the composites, and I will take time for 10 minutes of 20 minutes of questions.
So George is asking, where can we get this? Are you talking about the piezo, or are you talking about the file?
What do you want?
Spreadsheet. Can we get a copy of the spreadsheet?
Of what I've presented?
The spreadsheet. This spreadsheet that you are showing.
Yeah, okay, I will send you. It's here, and it's here.
Okay.
Just have to this is quite a simple point of view. This is analytical. This is not perfect, but this is a way to compare the stiffness.
Hello.
Yeah.
Thank you.
Welcome. B10, 12, and 14, it's not a formula. It's the values that you measure. Because this is what I have measured. And when you use a piezo with the card, with the Sonic Visualizer software, I will show you how it looks. Yeah.
Romain, apparently you didn't give the permission to access the spreadsheet, so you shared the link, but
okay.
It's in partial.
I will share another link because this is with my work. Yeah. I will have a lot of mail that request access. All right. Yeah, I will make the same on my personal drive. So it will be, there is no limit. I will send you another one. But of course, this has to be combined with a tutorial, of course. This was just an example. The aim was not to provide you a tool right now. But yeah, a 2-page tutorial and it's fine. Yeah. Here's another one, and I will send you the other one. All right. I can the 3D file for the neck angle jig. Yeah, I will share the 3D file for the neck angle jig. No problem. It's made with FreeCAD, so it's a free software, so there is no problem of license anyway. Just send me a private message. So if you have a 3D printer, it's fine. Ah, it will take a bit more time, but I will send a new version. Yeah. Of course. Do you have any questions? There's a lot of questions. Okay. Yeah. You have questions?
Yes, I do actually.
Yeah.
Hi, Romain.
Hi.
Thanks for the talk. I was particularly interested in the time domain impact propagation.
Yeah.
And I think you mentioned that it was 1 millisecond.
Yeah.
Is that correct?
Yeah, 1 millisecond, there was already a lot of mess and a lot of interferences and reflections.
So if I understand correctly, the millisecond was the time that it took for the standing waves to interact with each other.
To interact with each other. Because it's pretty simple. The speed the wave propagation in the direction of the grain is like 5,000 meters per second.
Right.
So in 1 millisecond, nearly 5 meters.
Yeah.
Nearly, because it depends on the shape and all lot of things, but it's the order of magnitude.
Okay.
And when you have, for example, a wood part, just wood, a plate, it's an ellipse because it goes fast. It's faster in the longitudinal direction than in the radial. And so at 1 millisecond, it's already a very big mess.
Yeah.
Can I?
Yeah, Colin.
Are you hearing me?
Yeah, I hear you.
The interesting thing about, I mean, wonderful talk, but the really interesting thing about the short time transients is that what you're actually seeing when you, for example, tap the violin, you're exciting all the modes of the violin. And they all come together right at the very beginning, and then they propagate. And what you're seeing is the interference. It's just another way of looking at it. The interference of all the normal modes, like when you tap a string, you excite all the string vibrations. When you tap a plate, you tap all the body vibrations. To start with, they're all concentrated where you tap it, but then they get out of phase with each other, but you've excited all those modes, and they include their standing modes too. So they're the actual modes that you actually see, and you're seeing the beginning interference. But I do think there is something about the normal, it's interesting that correspondence, because that's how many people actually do measuring the admittance and everything else like that. When I look at, for example, the sound that's vibrated very early on, the initial transient, you see modes in, if you do look at the frequencies, you see a large, wide range of modes that aren't actually the standing modes as well. Yeah. I think that you excite all sorts of modes, every single mode of the thing, including, for example, longitudinal modes, and they all contribute to what happens at the beginning, but they become less important as you go on. So when you take the way of measuring it, when you take the whole signal, the very start of the signal is different from all the normal modes that you actually see. There is an initial transient that comes from all sorts of things vibrating that don't really matter in terms of the acoustics.
Yeah, and
agree with that.
And they are not resonating, so they are not sinusoidal. second, so they are not, when you perform an FFT, you don't see them.
Yes, it's like when you hit a drum. When you hit a drum, you get all sorts of modes that are coming from the support system. So at the beginning, but that's different from the modes of the membrane itself, which is giving the sound.
Romain, I was just really curious about another thing you mentioned. Which really surprised me, which was that the dynamic behavior of the body, the wooden body, is not affected by the tension of the string. But I was wondering in that context, because you spoke about lateral pressure on top of the bridge, but did you measure the longitudinal compliance of the strings or the flexibility of the strings?
On the measurement?
Yeah, do you remember?
No, on the measurement, I only measure the dynamics of the body.
Okay.
And I have changed the tuning, the pitch of the string by lowered by 1 octave, which is quite high in terms of tension. And I have not observed a difference on the eigen frequencies.
Yeah, I understand. Thanks.
I would concur with that, because my measurements to the internal sound, which is measuring all the notes as well. The effect of the string tension is remarkably small.
Yeah, very, very small. Very small. Because
when you actually just take a G string on a violin and tune it, take it away, or even 2 strings, you really don't hear any difference on the other strings.
That's the fact. When you mute the other and you tap, you don't. The idea is that you don't hear a difference. That's a, but the bridge may be when you, for example, most of a lot of makers tell me, well, on the cello when I change the angle, the sound changes. Okay, but maybe it changes because the neck, the string angle is not the same, exactly the same, rather than the fact that you apply more pressure on the soundboard. So we have to check it. We have to check that the difference in sound doesn't come from the difference in boundary condition of the strings, which are quite important, because, for example, on a guitar, you change the boundary condition, you have a guitar, then you have a sitar, if the saddle is not good. So it's very important, the boundary condition. So when the neck angle changes, the boundary condition of the string changes. And if we don't see difference in the dynamics of the body, maybe that the answer is that the string doesn't vibrate the same if its angle changes on the.
Can you explain what you mean by the boundary condition changing when the string angle changes?
When you have a string that is, it's called a standing string, because the string is not clamped, the string is not fixed. It's resting on the saddles, top saddles on the bridge. And so when you change the equation of motion of a string depends mainly on the boundary conditions of the strings. If it's fixed on one way or on the other way, if it's resting on the saddle. But so the way the string is on the saddle, which is a boundary condition, is quite important in terms of damping, in terms of, because you have to imagine that the strings hits each saddle more than 100 times per second. So the exchanges in terms of energy, in terms of everything on the saddle is very important.
Yeah, but how does the angle of the strings over the bridge affect that boundary condition?
Because the string is not in the same. The contact surface is not the same. A lot of things are not the same when the angle changes. Colin, you want to say something? You're mute.
You're muted.
You're muted, Colin. We don't hear you.
Well, is Jim there?
Yeah, we hear you.
Jim Woodhouse?
I don't think he's here.
No, okay. It takes us back to the banjo talk, because on the banjo, which has a much more flexible membrane, in a certain, you might think, actually, it's amazingly rigid, because if you press down, it's really quite strong because the tension's so high. But with the banjo, there is a force that comes from the break angle. That is, the strings as they come over and the after length, they're at really quite an angle. And when the bridge goes up and down, it extends the length of the total string length, and that is the component that then acts downwards. And that certainly, almost certainly contributes to the sound of the banjo. And it may do so also for the bigger instruments, because if to the scale of the instrument, if the top plate is more flexible than, for example, the violin's quite small and really quite, got really quite a high arching compared to the cello. It's much easier to press perhaps down in the bridge direction, the force acting down. And it could be important, and more important for the larger instruments, like the cello and double bass. So there's a rational reason why it might be different than from a violin.
So you're meaning that with a cello, you expect more differences if you change the strings tuning?
I'm saying it might be possible. I mean, it's due to the relative restoring force of that downward force from the bridge of the going over the break angle, compared to the strength when you press just the membrane down itself, as it were. That's not the membrane, but the plate. But I mean, it's an interesting question, and one which we could easily measure.
Just one quick question, Romain. Just your piezo element.
Yeah.
In your calculations, in your spreadsheet calculations, do you take into consideration the mass loading of that thing? Because it's pretty heavy.
No, I don't take this into account. It's pretty heavy.
Or you don't need that. Yeah, it is pretty heavy, I think. It's made of brass, isn't it?
It's, yeah, it's brass. It's like 0.5 gram, I think. I will have to weight it. On the plate that is like 200 grams. The idea is to have the repeatable. It's not for an absolute value, it's for relative values and evolution values.
It doesn't really matter that much.
It's on a full plate. And so, of course, on a very thin plate, very small, this can be more influential.
Okay. Romain,
yeah.
Thank you for sharing your inspiring work. And I'm wondering if you have done any work on how material properties might influence geometry. In other words, one gets the sense that the geometry of the violin as it currently is sort of optimized for the material characteristics of wood, of spruce and maple. And we wonder how, if say we're using alternative materials, say carbon, just for example, how, I wonder if, does the geometry want to change if we want to optimize for using carbon? I think of, like, for example, when the bicycle frame was optimized for steel, when aluminum and carbon were first introduced as alternative materials, they basically made steel bicycles but out of aluminum, and they didn't work very well.
Yeah, so of course there is a link between a material and the way you put it into bring it into a geometry. Of course, carbon has, carbon is not a material in itself. It depends on how you use it. You use it with different cores, different kind of fibers, like this fiber, for example. So this is flax fiber, and we try to mimic the same behavior of wood. So in this case, we don't have to change the design. But yeah, if, for example, you want to have the same 10 first again frequencies of a violin body, and you say you don't use spruce, but you will have some other material, some other species, it's possible to evaluate what would be the best arch and thickness to have the same frequency. This is an optimization if you know what you want to be the same. But if you want to have something different or better with a lot of, I don't know what this means, better, but if you want to have something else, it cannot be used to say, with this kind of optimization, you will have a better sound. impossible to use it for that.
Yeah, I think what I thank you for the correction. I think what I was referring to, if we want to recreate some of the same modes that we are used to hearing in the violin sound, how, if we are using an alternative material, how might the geometry want to be different, if anything, from the geometry that we know tends to, the ranges that we tend to know work for the traditional materials? Yeah.
Yeah, well, the virtual prototyping can be a key tool for this purpose, yeah. Because it can enable you to win some time. Yeah, I've not presented something, but I have used virtual prototyping to find the best, the recipes of composites that would be closer to wood. So the idea was like, if my guitar plate was made in wood, it would have the 10 first eigenfrequencies values and the shape. So the idea was to use a model with a lot of computation, with different kind of architectures of the composite, different orientation of the fibs, different cores. And the aim was to obtain a recipe that would give the same eigenfrequencies that if my plate was made of wood. So this is an application, especially for the material. And yeah, this is what we have done for the piano soundboard. So the piano soundboard, the first mode is at like 5 or 6 hertz in free conditions. The idea is like, how can I use a veneer plus different fibers plus a core to have the same frequencies? That objective is to have the same thing than wood. We are not pretending to have something different or better, to have the same thing than wood. In theory, it may work. Then after, we have to make a lot of tests. So we'll be making it with different kind of instruments. And at the end, be sure that whether musicians make 2 different sets of instruments made of wood or made of composites.
John, you spoke about the geometry, but I've made a lot of really crazy looking instruments, and they, like for example, this one, which is based on a kind of 20th century architecture as opposed to Renaissance architecture. They all sound incredibly violin-like. So most of the character that we know is actually coming from the behavior of the bow and the reaction of the strings to the body. And even those signature modes are not quite exactly in the same spot. The violin character is incredibly overwhelming.